Hi there, hope all's well with you. So, we're going to do lecture D. Thank God there's no D.1 or D.2, there's just D. This is a really, from my personal perspective, a very interesting lecture because all that you've been doing earlier, matrices, vectors, quasi concave, quasi convex, all that stuff is going to come together in optimization. Uh, in pretty much any course you take in grad school, micro, financial economics, finance, investments, portfolios will involve optimization. So let me try to motivate. It's this lecture is very intuitive. If you get the intuition, you're 99% done. The math is easy once you get the intuition. What you have here is a typical example of what you doing in real life with optimization. So let's pretend that a company is selling a product that has a linear demand curve. Baby A is the highest price customers are willing to pay. Baby B is the absolute value of the demand curve slope, which you know has something to do with price elasticity. As you've discussed in the previous lecture, you can describe the demand curve in several ways. It's same equation on the right side. The left side just tells the reader what you're trying to emphasize. So just to remind you, if I say f of q, it means that you're emphasizing price depends on quantity, and you're sort of subsuming the role of parameters A and B. But if you want to highlight the role of parameters A and B, you will then write it as function of quantity, semicolon, the parameters A and B. Now, same thing with revenues. You can express them in terms of Q or Q and the parameters A and B. So let's start with optimization. In this course, we only do maximization problems. I'll explain in a few seconds what to do if you come across a minimization problems. It's really important, guys, especially if you're a math major. Whatever you learned as an undergrad may have to be modified in this course because in this course, the entire interpretations of Lagrange multipliers depends crucially on you setting up solving max problems in a very particular way. So for those of you who've done this as an undergrad, you'll see what I mean by in a few minutes. For those of you who haven't, just pay attention. Alpha is a set of parameters, and there are four basic classes of optimization problems in this course. One is unconstrained maximization problems. You're choosing a value of x to maximize a equation of y, which depends on x and set of parameters. Parameters being those a's and b's behind the scenes. Because remember that in any given optimization problem, those parameters may be constant. Think of demand curves, intercept, for example. But you realize that in the future, the demand curve intercept could change. As the parameters change, the value of x and y could change. So you want to emphasize roles of both the variables and the parameters in these problems. You could have equality constraint maximization problems where you're trying to maximize an equation of y, but you're insisting that for the time being, some function of x, if it helps you, you can think of it as x, simply x, must be equal to a constant. Then it comes inequality constraint problems. You're trying to maximize a function, but the constraint now says that some function of x, gx, for example, x, simple plain x could be asked to be less than or equal to a constant c. And of course, you can combine the two, where you have both inequality and equality constraints. Obviously, I've given you very simple problems with only one equality, one inequality, and same thing here, one inequality, one equality. So the idea of these constraints right here is always refers to things besides the domain. The domain is in some sense always a restriction on the axis. When you say the words constraints, you mean something besides that. So either there has to be some relationship in terms of x that must be equal to a constant or less than equal to a constant. As I said 2 seconds ago, the entire lecture is based on you solving maximization problems. So anytime you're given a min problem, you've got to turn it into a max problem. And that's done very easily. Here you're asked to choose a value of x that minimizes the value of z. Notice that if I multiply the objective, which is right here, by -1, I flip the function. So instead of trying to minimize z, I want to maximize y. So you can easily turn a min problem into a max problem by multiplying the objective by minus 1. Notice that even for equally constrained problems, I want to minimize z subject to x is equal to 8. The x star that I get, the x star here, was the same x star whether I minimize z or maximize y. The x star I get here is the same x star whether I minimize z subject to x is equal to 8 or maximize y subject to x is equal to 8. So you only multiply the objective by minus 1. And same thing here, you flip the objective. The x star that minimizes z subject to x star less than or equal to 8, the same x star that maximizes y subject to x being less than or equal to 8. Again, simply multiply the objective by minus 1. So now that we know how to turn min into max problems, let's roll. To sort of motivate what comes next, imagine that you're solving a revenue maximization problem. So I take these 4 classes of problems you saw earlier and try to give you some intuition behind what's going on by using revenue maximization. An unconstrained problem would imagine that your factory, your plant, your company has no capacity constraints. There are no minimum production constraints, there are no price controls, none whatsoever. And your only task is to choose quantity to maximize revenues. Whatever answer you get for quantity, whatever answer you get for revenues is ultimately going to depend on those A's and B's you had behind the scenes. Now you want to maximize revenues, and let's say you have your manager, perhaps a Rotman MBA, also known as many bitching assholes, right? Insist that your factory always produces 100% capacity. So you insist that quantity be equal to capacity. With this equality constraint, it's not surprising that the answer is going to be Q is equal to C, but whatever it is, you realize that the answer for quantity and revenues again depends on those alphas, those A's and B's, the demand curves and revenue functions, and the capacity constraint C over here. And these are, of course, quantity subject to constraints, revenue subject to constraints. Same thing with inequality. You could insist, maybe an MA or MFE, a bit wiser than MBAs. MBAs would say all planes should fly full. All parking garages must be full. Not true. The smarter person would say, no, quantity must be less than or equal to capacity. It might be optimal for you to actually have some empty hotel rooms, empty for airline seats, because it depends on the current demand conditions. With that, with this inequality constraint problem, again, the answer for quantity and revenues will ultimately depend behind the scenes, possibly on alphas, the A's and B's, and the C's. And same thing, of course, with the mixture. So you'll notice that the answer that you get for the quantities, which I'm now going to call, for lack of a better word, the X stars, and what I was trying to maximize was revenues, my objective, which, for lack of a better word, I'll call the Y star. So the X's are your quantities, intuitively, and the Y's are your revenues, what you're trying to maximize. So just to reiterate and reinforce this idea of why the Q's and the R's and the X stars and the Y stars change when the A's and B's change, take a look at this demand curve. Initially, it was 10 minus Q. The highest price we were willing to pay was $10. For whatever reason, advertising, I don't know, has become hip. Maybe this was a feature on TikTok. Maybe it is TikTok. All the customers now want to pay 10 cents more per unit. The demand curve shifts up, classic a la Echo 100 micro, right? And now this also causes a change in revenue. So the quantity that maximizes revenues is now going to change, as is the amount of revenues that you make. So the X stars are changing, the Y stars are changing. If I change the B coefficient, which now means the demand curve is now in this particular case steeper, again the X stars, which mean quantities, and the Y stars, which mean revenues, are going to change. So you can see the X stars and the Y stars ultimately depend on the parameters behind the scenes. Which means that as you study this lecture for a glorious test on Friday, you want to say to yourself, where am I headed? And what 4 things do I need to know for any optimization problem? You need to know how to solve for the X stars, the solution. That's called first order condition, or FOC. You also need to verify that the X star that you have is indeed the solution. It's a maximizer, not a minimizer. Second order condition, or the SOC. SOCs are painful. I hate SOCs. F double primes, Hessians, blah, blah, blah. So one wonders rhetorically, listen, do I always have to, the second I find X stars through first order conditions, do I always have to find second order from second order check? It turns out, not always. And then as you just saw right now, your very x stars and your y stars themselves depend ultimately behind the scenes on those parameters a's and b's, just like the previous example right here, right? Your x stars and your y stars all depend on those parameters a and b's. But those a's and b's change, your x stars and y stars change. So one wonders, without having to redo the problem, is there some technique for finding out or forecasting the change in the x stars when some parameter changes? And by the same token, the change in y star when some parameter changes. As long as you get this intuition, we're golden. Let's start with a single variable function unconstrained optimization. Here are two examples. Here's a function. Notice I haven't told you what the equation is because I'm lazy. All I tell you is that his domain -2 to +10. So x can only take values between -2 and +10. Excuse me. You can see the graph wiggles, wiggles, wiggles up and down. And now you're asked to find the maximum. You realize that there are local mins in this neighborhood. That's the min point. There are local maxes, right? In this neighborhood, that's the max, etc., etc., etc. But the place, the highest place, the solution, the maximum point is right here, which just so happens to be also a point where the slope is zero, and that's called a stationary point. Stationary points are where the slope is zero. And by definition, stationary points can only happen when x takes on a value in the interior of the domain. Right? So you can see this because over here, notice how the solution is not at any stationary point, not the slope is zero, but rather at this place right here, where the slope is not zero. In fact, the derivative is not defined at all. In fact, strictly speaking, it's defined at the right, but not left and right. And this is a boundary point. So you realize that the solution that you're looking for could be a place the slope is zero. And if so, the x star is going to be the interior solution, interior because it's in the interior of the domain, or it could be on the boundary of the domain, and hence the expression boundary solution. Right? So given this possibility, here's what we need to do. Once you realize that you could actually have a boundary solution or interior solutions, and interior solutions are where you have stationary points or slope is zero. Here's the algorithm. Take a look at this function right here. In the old days, I used to use Excel and demonstrate how Excel makes mistakes, but I don't have time, neither do you. How would you solve this thing by hand? First, you'll find out the value of y at all stationary points. Take first derivatives, 2x minus 2, set that equal to 0. You're looking for stationary points, and the only stationary point here is x is equal to 1, at which point y takes the value of 9, right here. Then calculate the value of y at all boundary points. So I'll set the value of y when x is equal to 1.5, which is 9.25, and the value of this function when x is equal to 0, the value is 10. And I'm going to ask myself which of these is the highest number, 9, 9.25, or 10. Well, obviously 10 is the highest number, which means the solution is at the boundary where x is equal to 0. So going forward, you realize that solution could be interior or at the boundary. So here's a general procedure for solving a single variable unconstrained optimization problems. Begin by stating the problem. Find all stationary points. These are your quote-unquote places inside inside the domain, where maybe there are places where the slope is 0. And of course, I just noticed a typo. Great. This should be f prime x. This should also be f prime right here. Okay, so you're looking for places where the slopes are 0, and if you find such a place, you may not find a place the slope is 0, but if you do find a place the slope is 0, how would you know it's a max and not a min? You know, and I know you've taken second derivatives and find negatives, but let's actually try to utilize what we've seen in the past lectures. Imagine that y is equal to, so the value of y depends on a function and the value of x. Imagine changing x a tiny bit. What would the change in y be? By total differentials, the total change in y is going to be equal to the partial derivative of f with respect to x times the total change in x. So what you've done is imagine you're at a certain place in the graph. X wiggles a tiny bit. This gives us change in y. And now let's change x one more time and ask what the change in y is going to be. So I now want to know what the change in y is going to be. But same logic as before, you now differentiate the f function one more time with respect to x, and now realize that x is now changing, so there's another dx. And by the way, that dx was left from previously. These are the same dx's, by the way. This gives you d squared y, f double prime dx squared. And now ask yourself the following question. Imagine you're at the top of a mountain. If x changes a tiny, teeny little bit, the total change in y has to be zero. That's what gives you your first order condition. But if it's a maximum, the top of the mountain, it must mean that if I move in any direction, north, south, east to west, the mountain must go down. You're imagining you're at the top of the mountain. So therefore, what's the change in the change of y? If I'm at the top of the mountain, this change in y should be a number that's negative because it'll be sloping downwards in all directions. That means the second derivative must be negative because dx squared is the positive number. So if the second derivative at x star, what's x star? The place where the slope is zero, a stationary point. If the second derivative of stationary point is negative, you know that you have a local max. And of course, you realize it could be this is only a local max, not the global max. So you worry about is the solution at the interior, boundary, and of course, you can use the algorithm we showed you the previous slide to see whether it's a boundary solution or interior solution. But of course, we ask the rhetorical question: are there any circumstances where simply finding a place the slope is zero is good enough to tell us that that's in fact the solution? I don't have to do all this stuff. I don't have to do second order checks, nor do I have to find possibly boundary solutions. When do I guarantee that a stationary point is in fact the solution? In plain English, if I found a mountain top, how do I know that's the only mountain top and there are no other mountain tops? It's very easy to answer this question because look at the intuition right here. You found a stationary point, a place where the slope is zero. Here's one example right here. Here's another. Here's another. Here's another. How do you know that's the only mountain? How do you know this is the only peak and there are no other peaks? How do we know this curve will never get back up again and go up again, right? Well, if I knew the function is strictly concave, and now I'm going to cheat a little bit. If I knew the second derivative is always negative for all values of x, not just at the x star, so if the second derivative is always negative, I know the function is strictly concave. And strictly concave functions look like this. Remember, the arc always lies below the curve. And once it starts going down, it'll keep going down forever because that second derivative is negative for all x's. It'll never come back up again. So if I found one mountain top, it must be the only mountain top. Similarly, if I have a concave function, if I found a flat point, it must be either one of many flat points at the same height or the only flat point. So this tells you why. Are there any places, any circumstances with a stationary point, a place where the slope is zero, is in fact the global max, or what are the global maxes? Yes, when you know the function is strictly concave or simply concave. So if you knew the function was called strictly concave to begin with, or concave, once you find an x star, you don't have to do the second order conditions nor look for boundary solutions. All right, let's now do comparative statics. This is really important because you're now bringing together all previous lectures. You understand that what you just did right now was you solved an unconstrained optimization problem. You looked for an x to maximize y, and you realize those pesky little parameters, those a's and b's. You've solved the problem. You found a stationary point, right? You wonder, how will that x star change if those a's and b's change? How will the y star change if the a's and b's change? Let's focus on the x stars for the time being. If the change in the parameters of those a's and b's changing are massive changes, you cannot use calculus. Then you're better off redoing the problem scratch one more time. So things like a 15% change in the parameter A or B. But if it's a tiny change in the parameters, 5%, 3%, 2%, then you can exploit either this technique in green, Let's read it out. This says you want to know how x star changes when some parameter alpha changes. Why not express x star not in terms of numbers, but in terms of those a's and b's, and then differentiate the x star and rearrange to get the answer. Here's how it's done. You have a curve. I was trying to solve for x that maximizes the value of y. Initially, I was 10x minus x squared, which is, where is it? 10x minus x squared, the blue thingy. See, blue. And the solution was x star. Now we change all the parameters. This thing goes up by zero point 0.1 units. The whole function y changes and gives you a brand new value of x. Without having to redo the problem one more time, is there some apparatus, some technique I can use from the get-go to forecast a change in x star due to a small change in this parameter? Yes, I can, because notice that this function is of what type? Ax minus bx squared. And what has changed over here? What's changed over here is, of course, the parameter a. So in this particular slide, I'm doing example one. One wonders how the parameter x, how the variable x star, the solution, changes when the parameter a changes tiny bit. What you want to do is, once you express the objective in terms of a's and b's, express the solution also in terms of a's and b's. For that, you need to take FOCs, first order conditions, solve for x star, and you should now say, well, wait a second, how do I know this is in fact a global solution? Well, if this is going to be the global solution, this must be the only amount on top. If that's going to be the only amount on top, this function had better be strictly concave. So if I could make the second derivative negative for all values of x, that would be the only answer. What is the second derivative? The second derivative is minus 2b. And therefore, that would always be negative as long as the parameter b was strictly positive. So as long as baby b is strictly positive, this is going to be a strictly concave function. That's going to be a unique solution. And now what I wanted to find out was, how does x star change when the parameter a changes? This is where people get really confused, because they're not used to doing, they're used to doing dy dx's. They're not used to doing dx something else. You want to know how x star changes when a changes. Why not differentiate x star with respect to a? So holding everything else constant, the answer is 1 over 2b. Now cross multiply. The total change in x star is 1 over 2b times the total change in a. And if you want to now predict using these numbers, b was initially 1. The change in a was, it went up by 0.1 units. So therefore the total change in x star is going to be 0.05 units. Over here, the parameter b is changing. See, b. And therefore, what's the change in x star due to change in b? Differentiate x star with respect to b, you get minus a 2b squared. Rearrange, the total change in x star is this expression right here. Sub in the initial values of a and b, and how much b changed by? It changed by 0.1 units. The total change in x is going to be negative 0.5, which means it went down. You know that this is also an equation for a simple linear demand curve revenue maximization. If you think in terms of micro, you have now just developed a rule for what's going to happen to quantity as the highest price people are willing to pay goes up and as the demand curves become steeper. If the highest price people are willing to pay goes up, the revenue maximizing quantity must always go up. This number is positive. And if the demand curve becomes steeper, the revenue maximizing quantity must always go down, because this expression is positive for any, of course, positive changes in A and B. Now we say, wait a second, could I do it a different way? Could I do it by implicit differentiation? So to do it by implicit differentiation, you notice the following. Let's do in general form first. What you solved 2 seconds ago was in the equation of y in terms of x and some parameters listed separately. You had a stationary point, which you found by taking dy dx, and you took partial derivative of this thing right here. Well, not partial, sorry. You differentiate the f function with respect to x, which is right over here, and you set that equals 0. Intuitively, if you were to solve this problem out, you would find x in terms of the parameters, those a's and b's and so forth, just like you did several slides back. You found the x in terms of the a's and b's. But now, if you look at this very carefully, this is in fact nothing but an implicit function. It is in fact a function of x's and the parameters. So why not rewrite this as an implicit function of x and parameters is equal to 0. Now, if I knew x star in terms of the parameters, just like it did over here, and someone said, how does x star change if a's and b's change? You could do direct differentiation. That's exactly what you see here. I could do direct differentiation. Or if I wanted, and if that's not possible, if I don't have an explicit expression, or if I want to, I could use implicit differentiation. That says the following. This expression by definition must be 0 at the stationary point, right? The solution to the problem. If that stationary point changes a teeny tiny bit, I haven't put x stars here because the notation will get really clumsy. But at the solution x star, this equation is 0. If I wiggle x star a teeny tiny bit, what's the total change in big F going to be? The total change in big F is going to be take partials of big F with respect to x, multiply by change in x, plus partials of big F with respect to the one parameter alpha that's changing, times the change in the alpha. But because it's a first order condition, this is you're imagining very tiny changes in the parameter. For tiny changes in the first order effect, there should be no impact on that slope. It's still going to be that first order condition is still going to hold with equality of 0. So therefore, the total change in this expression must be equal to 0. Remember, you're imagining infinitesimally small changes. And therefore, this expression being equal to 0, you can see that dx over d parameter must be equal to minus the f equation, which was this one, differential with respect to the parameter alpha, and the f equation, which is this one, differential with respect to the variable x. Let's see an example. Let's do the example one more time that you saw a few minutes ago. Ax minus bx squared. I know that if I look for a stationary point, I would do so by differentiating y with respect to x. I know that I have, this is my answer my first order condition. This implicitly defines, this is an implicit function of x and those a's and b's. In this case, I do have an explicit solution. If I did want to find out how x star changes with respect to a, I could do direct differentiation, get the answer. But if I want to use implicit differentiation, the previous slide says the change in x star due to the change in a is found by doing this thing. So differentiate this f function with respect to a. What is this f function? Here's the f function. If I differentiate with respect to a, the answer is 1. That's down here. And now I need to differentiate this f function with respect to x. Take this f function, big F, differentiate with respect to x. And the answer is minus 2b over here. So minus 1 over minus 2b, 1 over 2b, exact same answer as direct differentiation. In the case of small change in b, same thing. I would differentiate the big F function with respect to b, which in this case would be minus 2x, and then divide by the big F function differentiated with respect to x, which is minus 2b. The minus and minus go away, so you're left with a minus here. 2 and 2 go off to heaven. X over b over here. But x was a divided by 2b, so when you simplify, you get the exact same answer as direct differentiation. Pretty cool. You now come to the other part of the coin. When the a's and b's change, yes, they cause a change in x star, but they also cause a change in y star. How can I find a change in y star? When the a's and b's change a tiny bit. Again, just like you did before, you could, just like you express x stars in terms of a's and b's, you could express y stars in terms of a's and b's. Let's do it that way. Same example as before, so I won't bore you with that same description. Same recognition that these equations belong to class ax minus bx squared. The solution is x star is a over 2b, which is a unique solution as long as b is a positive number. Now, what you want this time is you're not asking how x star changes when the a's and b's change. You're asking how the y stars change when the a's and b's change. So what the previous slide said was express the y stars in terms of a's and b's. To do this, I need to evaluate the function y not at any x but at x star. So I'll put x star here, x star over there. But x star I know is a over 2b. When I sub in the values of x stars and simplify, I get this thing right here. So anytime you express the y star, what you're trying to maximize Anytime you express the objective function in terms of your parameters is called the value function. And now in this particular example, you want to know how y star changes when, let's say, baby A changes. Differentiate y star with respect to baby A. The answer is A over 2b. What's the total change in y star? Difference in these two y's over here. Cross multiply, sum of the initial values of a's and b's times the change in a, which was zero point 0.1 units, and the answer is when a goes up by 0.1, y star goes up by zero point 0.5 units. In the same way, if you want to know how y star changes when baby b changes, differentiate y star with respect to baby b, rearrange, sum in the values, and this tells you that when b goes up by 1.1 units, y star falls by 2.5 units. Again, the idea here was you're expressing the y stars in terms of a's and b's. However, this is tedious because imagine a very complicated objective function. I'll show this one to you in a few minutes. If this is a really long equation, you really wouldn't want to sub in x stars and simplify and so forth. So what you have instead is one of the most beautiful theorems in mathematics. You don't know this, you ain't going to pass the test. Called the envelope theorem. The envelope theorem is doing exactly what you did right now, but much more efficiently. It's telling you how y star is going to change when some parameter alpha changes. I'll read it out first, and then I'll read out one more time by example. It says, whatever your objective function was, express it and solve that problem in terms of a's and b's. Find the x stars in terms of a's and b's, set it aside. Go back to the original problem. And I stress this because what you're not doing is here, you are subbing x star back in the y function to get y star. That's not what you're doing here. You simply go back to the original function expressed in terms of a's and b's. You take that original y function, not y star, the original y function, and you differentiate that with respect to the parameters changing. Once you do this, whatever you see, if you see x on the right side, you express as x stars, and then you would get the change in y star due to change in parameter. Let's follow the steps one more time. Here's an original problem, a new problem. Somebody says, give me the change in y star due to a change in baby a, without having to calculate the value function or doing the problem one more time. Express the objective and solve the problem in terms of a's and b's. Expressed, solve in terms of a's and b's. I've now set aside the x star here. Cool? In terms of a's and b's. This is the most important step. Go back to the original function in terms of a's and b's. Here it was. And now what you say is differentiate that function with respect to the parameters that's changing. So what was changing was the parameter a. Differentiate this with respect to baby a, and the answer is dy dA is of course simply x. So therefore, when you cross multiply, so dy star over dA would then be equal to x star. So wherever you see on the right side an x, plug in an x star. And when I cross multiply, the total change in y star is going to be equal to x star times the change in a. Well, what was x star? A over 2b multiplied by change in a. And when you do the numbers, you get the exact same answer that you got by the value function approach. It's the exact same answer numerically. Another example, by b this time. If b changes, by the envelope theorem, express the original y in terms of a's and b's, solve the problem in terms of a's and b's, set this solution aside. If you want to know how y star changes when b changes, differentiate the y function with respect to b. So differentiate the y function with respect to b, the answer is minus x squared. And I'll cross multiply, and wherever I see an x, you put an x star. And when I do so, sum in the value of x star right here, and insert the values, I get the exact same answer I got by the value function approach. So the envelope theorem is much faster because you should appreciate what you're not doing. You don't have to take x star, stick it back in the objective function, and then differentiate. It's much cleaner and much faster. And to drive that point home, I'll show an example in a few seconds. Let me do the proof of the envelope theorem. Assume that you are solving a problem like this and it has an interior solution. As an example, ax minus bx squared. Since you're assuming it's an interior solution for this proof, do dy dx, dy dx. You know you're going to get an equation in terms of the x's and a's and b's, which must be equal to 0. An equation in terms of a's and b's that must be equal to 0. If you want, you could solve the x stars in terms of a's and b's. If you want, you can solve the x stars in terms of a's and b's. And now you realize that this function, this first order condition at the value of x star is going to be equal to 0. So if I take the first order condition and I evaluate at the value of x star, if I put literally x star back in here, this entire left side has to be equal to 0 by definition. Now, if you were doing the value function approach, what would you have done? You would have taken your x star and stuck it back in the original y function to get the y star function. You would have taken your x star right here, stuck it back in the y function to get the y stars. Right? Now what you want to do is you wonder how this y star changes when a parameter changes. So the total change in y is going to be equal to differentiate the f function with respect to x, multiply by the change in x. Sorry, alpha is changing. So the change in y, total change in y due to a change in alpha is the change in f due to a change in x, which means you differentiate the f function with respect to x. Then the change in x due to a change in alpha, that means x differentiate x with respect to alpha, times the total change in alpha. Plus, remember the alphas are coming separately. Remember the last lecture we did. The change in f with respect to alpha, that's your partial derivative right there, times the total change in alpha. In the same way, so you can see that over here, this is nothing, of course, but the first order condition, right? That's your first order condition right here. When I stick that in here, by definition, that first order condition has to be equal to 0. So the first term is going to go and become 0. What you're left with, of course, is in words, take the original y equation, differentiate with respect to the parameter that's changing. Take the original y function, differentiate with respect to the parameter that's changing, which of course is a. In that case, dy dA is of course going to be x, and when I evaluate at the opposite solution, that becomes x star. And then when this becomes the total change in y star is this thing times the change in parameter. In this case, x star times dA. To get the derivative, I now divide, and that's exactly what you saw earlier, right? So again, the envelope theorem says to find the change in y star due to change in alpha, simply take the original y equation and differentiate with respect to the parameters changing, and then sum in the values of x star, and then you'll get the answer. To show you how important the envelope theorem is, imagine that you're solving a Cobb-Douglas minimization problem. You're asked to choose the optimal amounts of labor and capital to minimize total cost of production, to make sure that what you actually produce is equal to target output that's bigger than 0. Welcome to grad school. Once you solve for the L star and K star, and if you then plug it back into this cost function right here, the optimal expression of L star, excuse me, sorry, and K star, you can think of this as your Y function. When you sub in those values right here, you will get your Y star. So your objective, your value function, is this nasty creature over here. So if somebody relied on value functions only, it would be a nightmare for them to say, how does cost change if, for example, the alpha changes? But if you use the envelope theorem, it will be much, much, much faster. At this point, you might be wondering, wait a second, so do we never use value functions? No, you don't use value functions. You always use the envelope theorem. Unless, of course, you're forced to use the value function. Here's an example. From Baby's Micro, you remember that this is the utility function of a consumer who perceives good one, good two as compliments, beer and beer. Actually, that's maybe not a good joke. Fine. Beer and chips, maybe, right? And the ratio is that for every unit of good number 1, you will have beta over alpha units of good number, alpha over beta units of good number 2. Okay. Subject to expenditure on good 1, good 2 equal to income. Intuitively, you don't need calculus to solve this problem. Since your utility depends on the smaller of these two numbers, the optimal solution is for you to have these numbers be equal to each other, right? Because you don't want any one term to be bigger than the other. You'd be wasting utility and also money. So the optimal solution, these two things must be equal to each other. So if you set alpha q1 equal to beta q2 and solve it together with this budget constraint right here, that's the answer for good one, good two. Now ask yourself, how would the optimal utility change if anything in this problem changed? So for example, the consumer faces price of good one, price of good two, and income, and alphas and betas. If any of these alphas, betas, P1, P2, and Y changes, what would the change in the utility be? By the end of the theorem, what I should be doing is I should be expressing my objective in terms of A's and B's, which I have done over here. But the end of the theorem then says what? It says differentiate the original objective with respect to the parameters changing. But I can't do that over here because this function is not differentiable. It's a min function. So I can't use the end of the theorem because the original objective function is not differentiable. But what about the value function? The value function says stick the optimal solutions back in the objective to get the optimal objective. So if I stuck q1 star, q2 star back in here, I would get the value function, optimal utility. And you notice something beautiful. Even though the original objective function was not differentiable, when you stick in q1 star, q2 stars, notice that these two numbers are exactly the same. The optimal utility function or the value function is in fact differentiable. So you can in fact answer the question, how does utility change if, let's say, for example, income changes? Simply differentiate. So I've shown you these techniques, how to find the change in x star, use small change in parameters by direct differentiation or implicit differentiation. And said if you want, unless you're forced to, you should calculate the change in y star, you change into some parameter by using Engel theorem. These techniques that I've shown you can be used for any class of problems. It doesn't not just for unconstrained optimization problems. So I'm not going to show them in the lecture. It's understood that down going forward, anytime somebody says that A and B has changed, you can always perform any of these green thingies over here to find the change in x stars or your quote unquote objective functions. We now go to a single variable equality constraint problem. Here's a simple example. You're asked to choose the value of x that maximizes the value of y, but you're told that x must be equal to 8. Here's the graph. Find the highest place on this mountain where x is equal to 8. You don't need a degree, and you don't even a master. In fact, you don't even need an elementary school degree to find out. If you're telling me that x is equal to 8, the answer is x is equal to 8. There's nothing to solve for. With one variable and one constraint, the solution is obvious. Yet, you may remember from undergrad that the way to solve these problems is by something called the Lagrangian method. So, what is the Lagrangian method? Meet Lagrange. The Lagrangian method says, yeah, in this particular example, I do know what x star is, but let me, for reasons you'll see in a few seconds, do something different. Let me rearrange the constraints. In this course, for the love of God, on Friday, don't forget this, if the x's must be on the left and the numbers must be on the right of an equality constraint. Once the x's on the left and the numbers on the right, rearrange it so that you have x minus the number is equal to 0. So you have to make sure the constraints are expressed this way. And then what you do is, originally you want to solve for one variable x. And now what Monsieur Lagrange says is, instead of maximizing this function of y, subject to that constraint, I want you to choose x and a creature called lambda to maximize what's known as the Lagrange equation that always in this course takes the exact same form. It never varies. Always write down the original y function, always followed by a minus sign, and lambda times the left-hand side of this constraint after you make sure the only number here is number 0. So in some of you in undergrad might have seen a different variation. You may have a plus here and the 8 will be here and so forth. Don't do this over here. There's a reason why we insist on the y term being first, always a minus, always a lambda, and always the left side of the transform constraint. A bit of warning, the Lagrange equation is not the same as Lagrange method. The Lagrange method now says, for some bizarre reason, you've now added a second variable. You've made my life more complicated. Instead of solving for an x whose value I knew, you are artificially introducing a new variable called lambda, and you seem to be solving a much more complicated problem. Well, the way it works is the Lagrangian method, which is only for equally constrained problems, says differentiate the Lagrange equation with respect to lambda, which I've done for you. It shouldn't take a rocket scientist to realize that if you differentiate with respect to lambda, there's no lambda in the y term right here. If you differentiate with respect to lambda, you're always going to get back minus this expression, which you know because of the constraint, behind the scenes, must be equal to 0. If x minus 8 is equal to 0, it spits out the constraint that x must be equal to 8. So it's a very clever way of saying, it's by forming this equation this way, Lagrange ensures that when you take first order conditions, you spit out the constraint that x must be equal to 8. Looking at this expression does not tell you that x must be equal to 8. It's only the act of differentiating with respect to lambda that you find out x must be equal to 8. You then also differentiate with respect to x. I've done it for you. Since you know what x is, it's equal to 8, you find that lambda is equal to minus 6. So now you have two answers. X is equal to 8, which was obvious from the get-go, and lambda is equal to minus 6, which we are not sure what in God's name that means. To appreciate what that means, let me now sub in the 8, the x star, and the lambda star back in the L function, the one that I was trying to maximize in the first place. When I do so, this expression is going to be your y equation subject to the constraint x is equal to 8. Here's a lambda star and so forth. So once again, this is your y star subject to the constraint x is equal to 8. This lambda is minus 6. In an equally constrained problem, this expression inside the square brackets must always go to 0 by definition. So the second term is always going to go to 0, and it's always going to leave you the first term, which is always going to be the y that you're maximizing subject to the constraints. So in general, whenever the L function is computed, it will always be equal to the value of the y star, the y, subject to the constraints, exactly as you see over here. So with this now, you can answer the question, why are we solving for lambda? Because one of the things this is a constraint optimization problem. And as a scientist, economist, financier, surely you would want to know, I've solved this problem, x was 8, y star was 16. Wouldn't you want to know how this y star is going to change if a parameter in this problem change? Well, there are three parameters, the a, the b, and the c. Of all the parameters, surely the most important one is parameter c. It's a constraint. So surely you would want to know how would your answer y star change if your constraint c changes by a teeny tiny bit. And you want to answer the question without redoing the problem again using calculus. So what if you're asked to compute the change in L star due to a small change in C, which you now realize is essentially, well, it is the same thing as asking how does the Y star subject constraints change due to a small change in C. And now, anytime you're asked to compute the change in the Y stars subject to due to a change in parameters, you use the envelope theorem. By the envelope theorem, I restate the problem in terms of A, B's, and C's. I solve the problem and express my solution in terms of A's and B's and C's. X star is equal to C, lambda star is equal to A minus 2BC. And once again, notice that even in this parametric form, it's obvious that the value of L star will be equal to Y star, where on the mountain you are, subject to the constraint that X is equal to C. If somebody wants to know how L star changes due to a small change in C, then it's simple by the envelope theorem. You go back to the original equation of L, right here, differentiate that with respect to C. When I do so, I get the answer is lambda. To find the change in L star, I now, whenever I see a variable on the right side, I put them in stars. And now since L star is the same as Y star subject to constraints, I have now found out the change in Y star subject to constraints due to a change in C is always going to be equal to lambda star. So the value of lambda star, this is why Lagrange is a genius. He set this problem in a way that not only would you get the answer of X star, but you will also get a number that tells you how the objective is going to change if you were to increase your constraint by a teeny tiny bit. The value lambda star literally represents the change in y star, the constraint y star, over the change in capacity or the constraint C. And in this particular example, it'll be equal to A minus 2BC. And incidentally, you should obviously notice that lambda star is going to be 0 when, of course, this expression is 0, which means C must be equal to A divided by 2B. And I'll come back to this in a few minutes. So one more time, just to drive the point home, you have solved this problem. You knew x star was equal to 8, and you know that y star at this point is equal to 16. You wonder if you were to increase the constraint, capacity constraint a teeny tiny bit, instead of making x is equal to 8, if it was something slightly bigger, what would the change in y star be? And the answer is, loosely speaking, for every time you change the constraint C by 1 unit, this y star will fall by 6 units. So loosely speaking, these are not small changes, but loosely speaking, if instead of saying x is equal to 8, you now said x is equal to 9, the y star would fall by 6 units. So y star would go from 16 to 10. Let's get ready for the next step. To do this, I want to point out that in an equality constraint problem, the value of lambda star can be positive, negative, or 0. To appreciate this, take a look at this graph right here. X is equal to C. So when x is equal to C, your solution is going to be here. In this region, this graph is upward sloping. All these lines are highly exaggerated. I wonder what will actually happen to the value of my y star if I were to bump up my capacity by a teeny tiny bit. If I change C tiny bit, and since x must be always equal to C, because the function has a positive slope over here, y star is going to go up. But since lambda tells me the change, so the sign of lambda, if lambda is positive, it means that y star has gone up. Since y star has gone up, lambda star must be positive here. In this region, remember the slope is flat here. For teeny tiny change in C, there'll be no change in x star. No change in x star means no change in y. No change in y means lambda will be 0. And for a teeny tiny change over here, increasing C teeny tiny bit, because the slope is negative over here, will make y star fall. Because y star is falling, lambda star must go down. So then an equally constrained problem, notice that lambda can be positive, 0, or negative. And when this is going to happen, notice that it's going to be positive whenever your capacity is below the unconstrained solution. So here's the unconstrained solution, right? So anytime your capacity is to the left, your lambda star must be positive. That's intuitive. Since you are below the unconstrained solution, there is some value to you of increasing C. If C just so by magic happens to be equal to the unconstrained solution, then lambda star will be equal to 0. There's no value in, of course, you changing C. But if C is beyond the unconstrained solution, in other words, you have too much capacity, which you're utilizing 100% of the time, and if you now increase the capacity even more, your y star is going to go down, so lambda star goes down. So coming back to that previous slide, 2 slides ago, when will this expression be 0? This expression will be 0 when a minus 2bc is 0, which means c has to be equal to a divided by 2b. A divided by 2b, my friends, is of course exactly the solution for the unconstrained value of x. So in a one variable, one constraint problem, what do we need to do? You set the problem this way, set the Lagrange equation, find stationary points by differentiating the Lagrange equation with respect to lambda and x equals 0. You don't have to perform a second order condition because think about this. You have one x, one constraint. So with that, you're simply literally picking off a point on the curve, right, on the surface. So there are no second order conditions to check when you have one variable, one constraint. Again, literally, you're picking a point on the Lagrange equation. So as such, there is no second order condition to check for. I'll explain more down the road. Now let's get ready for the next level up, which is inequality constraint optimization. So this is called the Kuhn-Tucker method. Tucker went to U of T, somewhere in the 1930s. He went on to become professor of mathematics, and along with Kuhn, he founded the mathematics of inequality constraint optimization, which obviously you now use in all of mathematics and physics and engineering and econ and finance and so forth. Tucker, by the way, is also the guy who coined the term Price's dilemma at Princeton. He was a colleague of John Nash. Here's a inequality constraint problem. Find the highest value. Please choose x to find the highest value of y, but this time make sure that x is less than or equal to 8. It's obvious from this graph that if I now am no longer forced to say x is equal to 8, x now can be less than or equal to 8. The solution obviously is over here, the unconstrained solution. And that's my y star subject to the constraint that x must be less than or equal to 8. And just like what Lagrange did, Kuhn-Tuckers also want to do the exact same thing. They want to give you a technique and algorithm that not only gives the answer for the x star, but also gives you a number called lambda that tells you how this constraint y star is going to change if that constraint c changes a tiny bit. To do this, they used to use the Kuhn-Tucker method. You first have to make sure that any inequalities are expressed this way. The x's on the left, numbers on the right, and these are less than or equal to inequalities. Don't express them as bigger than or equal to. So if you have a bigger than or equal to inequality, simply reverse it by multiplying both sides of -1. Once you do this, bring the numbers to the left, so the only creature on the left and right side is number 0. And once again, you form the Lagrange equation the exact same way as you did before. Legions of students have failed exams because they get confused. This is literally the same Lagrange equation as when there was an equality constraint. First term is always y, second term is always a minus, lambda, left-hand side of the constraint. So if you on Friday morning open your exam and you only see this question, you cannot solve it because you have no way of knowing if this corresponds to an inequality constraint problem or an equality constraint problem. Someone has to tell you prior to this what kind of problem this is. Excuse me. To solve this problem by the Kuhn-Tucker method, what you do is you, as before, differentiate with respect to x, but you do not differentiate with respect to lambda. Can you see why? Why wouldn't you want to differentiate Lagrange with respect to lambda? Quickly, why don't you want to differentiate Lagrange with respect to lambda? Because if you did, what would happen? If you did differentiate Lagrange with respect to lambda, you would get minus square brackets x minus 8 is equal to 0, which would then imply that x is equal to 8. But that's not true because x is supposed to be less than or equal to 8. You don't know right now whether x is equal to 8 or less than 8. Instead of differentiating Lagrange with respect to lambda, you write down the Kuhn-Tucker conditions. They always have the exact same structure. It never varies. In the world of Kuhn-Tuckers, in the world of inequality constraints solved by Kuhn-Tuckers, one more time, if you set it up according to what Kuhn-Tuckers do, y minus lambda, left side of constraint, where behind the scenes that was a less than or equal to constraint. In the world of Kuhn-Tuckers, that lambda will never be a negative number. It'll always be bigger than or equal to 0. So write this down. Nowhere in the system have you mentioned the constraint. Well, now you have to mention the constraint explicitly. X must be less than or equal to 8. And for reasons I'll explain in a few seconds, just like you did before, exactly as in the case of the equality constraints problems, this expression is going to be equal to 0. But when you had equality constraints, it was 0 because the terms inside the bracket was 0, because previously x was equal to 8. But now in the world of inequality constraints, the whole expression has to be 0. For reasons I'll explain in a few seconds. So one more time. Why don't we differentiate with respect to lambda? Because it'll force x is equal to 8. Lambda will never be negative for reasons I'll explain in a few seconds. State the constraint. And this last term will always be equal to 0, just like in equality constraint problems, but for different reasons. Here's why. You remember that lambda, if lambda is positive, it means y star is going up when you bump c up. And if lambda is 0, it means y star is staying the same when c goes up, etc., etc., etc. Now you have a different problem. x must now be less than or equal to c. If you made c a tiny bit bigger, because the slope is positive over here, your x star would go up, your y star would go up, and your lambda star would go up. And by the way, notice that this expression will be 0. Why? Because even though even though lambda is positive, x is equal to c, so this expression is 0. If the constraint just so happens to be equal to the unconstrained solution just under the top of the mountain, and if you wiggle c a tiny, tiny little bit, then again there will be no change in x star, no change in y star. That means lambda star must be 0. And this expression, because lambda star is 0, is going to be equal to 0. And if c is way beyond the unconstrained solution, if you wiggle, you know your answer is going to be x star right here, because now you have the option of being less than or equal to c. If you now bump up c a tiny bit, no change in x star, no change in y star. That means no change in lambda star. And then this expression will be 0 because lambda star is equal to 0. So what have you noticed? Lambda is either bigger than or equal to 0. It's never negative. And this animal will always be equal to 0. So that's why the Kuhn-Tucker condition makes sense. In the world of Kuhn-Tuckers, lambdas cannot be negative. It's physically impossible. And that expression will always be equal to 0. That's what you see over here, right? So if you utilize this, this gives you a very fast way of solving problems. Here's how we do it. You want to solve this Lagrange problem. You took first order conditions with respect to x, wrote out the Kuhn-Tucker conditions. On Friday, what you don't want to do is you don't want to start with this first term here, because that implies two inequality, two possibilities. Next, you don't want to bring this case here, because it implies another two possibilities. That's given a 4. What you want to do is you always want to start with the one expression that you know is always going to be equal to 0. That last term right here. This can be 0 in one of two ways which are not mutually exclusive. Either x is equal to 8 and or lambda is equal to 0. So what you're doing right now is you're conjecturing a solution. You're saying, I propose that the answer is x is equal to 8. Well, if x is equal to 8 is indeed the answer, it must satisfy all Kuhn-Tucker conditions as well as the first order condition. Let's check. Well, if x is equal to 8, this is already satisfied. This is already satisfied. And what remains to be checked or verified is whether lambda is bigger than or equal to 0 when x is equal to 8. For that, I go to the first order condition, stick in x is equal to 8, and find that lambda is not bigger than or equal to 0. In fact, it's negative. So there's no way the answer will be x is equal to 8. That leaves you the other possibility. So lambda is 0. If lambda is 0, this KT condition has to be satisfied. So all I have to do is verify whether x is less than or equal to 8. Stick lambda is equal to 0 in the first order condition, and voila, when you find out that x is indeed a number less than or equal to 8. In fact, 5 is less than 8. So the answer is x is equal to 5, lambda is equal to 0. So therefore, the answer is what you can see graphically anyway. If you solve this problem, the value of x star is 5. At that point, the value of the function is 25. That's the constrained value of y star. And if you were to change c a tiny little bit over here, teeny tiny bit, there'll be no change in y star because you know lambda star is equal to 0. Same interpretation as before. What about, again, with one variable and one constraint, there are no quote-unquote second order conditions to check for, right? Because you're literally, again, picking a point either where x is equal to c or where x is less than c. But that's it, right? There's literally no optimization to be done. So no second order conditions. Now let's go to the multivariate case. This is actually pretty easy. Now you have y as a multivariate function of x's, several x's. As before, if you're looking for stationary points, you would take the first order condition by setting the Jacobian vector equal to 0. Is that even right? I think so. Right? That's second order condition. Just like you did before, you want to establish the fact that at the top of the mountain, quote unquote, the mountain falls in every direction. But things get now much more tricky. Here's why. Take a simple 2x unconstrained optimization problem. Y is a function of x1, x2. Imagine both x1 and x2 change. The total change in y is the partial of f with respect to the x1 times total change in x1 plus portion of f with respect to x2 times total change in x2. So at a top of the mountain, this expression must be 0, right? Because dx1 and dx2 together are each 0 by the Jacobian. If I'm at the top of the mountain, then if I now change x1, x2 one more time, this entire expression, what's the change in that? I want that, the change in dy, I want that expression to be negative. But how do I calculate this? To find this change, I have to change x1, x2 one more time. So, but the same process, what logic as before. You take f1, differentiate with respect to x1 one more time, multiply with change in x1, and that's the same x1 that you see here, change in x1 here. Now, take the change in f1 due to x2, that's your dx1 from before, and now you have to change in x2, that's over here. Now, x2 is changing here. So find out the change in f2 due to a change in the first argument, which is x1, multiplied by the same dx2 that you see here, the dx1. Right? And then, of course, find the change in f2 due to change in x2, and then, of course, same change in x2 over here. So if I collapse all the terms here, I notice that I get something nice. It is a quadratic form, right? X transpose symmetric matrix. Why is it symmetric, guys? Because this is the matrix of second derivatives, the Hessian, which by Young's theorem you know is symmetric. And you can only sign quadratic forms if the middle matrix is symmetric. Now, if you want, as I start at the top of the mountain, if I go in any direction, I want the change in y to be negative. For that to happen, I need this matrix to be negative definite. Therefore, the way to find our second order conditions is evaluate the Hessian matrix at x star. If it is negative definite, it's local max. Just like before. When do you not have to bother doing second order conditions? When you know a priori or before the fact that the function f was strictly concave to begin with. That means that if you knew that if the function is strictly concave, you wouldn't have to check the second order conditions at all. In the homework as well, by the way. Here's an example. Here's a two variable example. Differential with respect to x1, x2. I should have done this in Jacobian form. Sorry, not Jacobian, sorry, gradient vector form. My bad. Here are the x's. Here's the y. You can easily compute the Hessian matrix, and I want you to sign it to determine whether this is indeed the solution. Well, yes, it is, because I've given you a 3D plot. So you can see that x1 is 100, x2 is 100, is at the top of the mountain. That is the solution. So, but you should find out that the Hessian at that point is indeed going to be negative definite. And by the way, I also want you to find out whether the function itself in the first place is strictly concave. I'm doing this for two reasons. If you want to find out if a function is strictly concave, you have to evaluate this Hessian matrix for all values of x. Whereas when you do a second order condition check, you're evaluating this matrix for that specific value of x stars, two different animals altogether. So here's another example or exercise. Again, I'll give this to you as an exercise, so you can do this on your own. Okay. Next up, what happens if I have an equality constraint problem with n Nancy variables, k constraints? I know it's crappy notation. I'm very sorry. These are constraints number 1, constraint number 2, k constraints. Each of them you see has an equal sign. Here's an example. So nothing magical has happened. As always, differential with respect to x1, x2, and lambda. Notice how the form of the Lagrangian is the y function minus lambda times left side of the constraint. And of course, these are the answers. Here's lambdas, here's the value y star. You know what lambda star means. It means that right now, x1 is equal to 500. If you now force x1 to be equal to 501, your objective would fall by roughly 800. Okay? You would go down the mountain by 800. What about go first order, second order, all that stuff? Well, when asked to solve a n variable problem with k constraints, you have to take the stationary points Lagrange equation. So you would have to find all the x's and lambdas that satisfy the first order conditions. And now, if you're given a certain x stars and lambda stars, how do you know that this is in fact a solution? I forgot to say this, I'm sorry. I should have said, how do we know the x stars and the lambda stars? I should not have said satisfying fx. I should have said satisfying else this system right here, the partial derivatives of the Lagrange function is a local max. The second order condition is checked using something called the border Hessian. It's a completely different border Hessian than what you've seen before, right? And before I present the border Hessian to you, let me remind you that under what circumstances do you not have to perform the second order condition check? When you know the function f is strictly concave, that's this thing right here, and the lambdas and g's are strictly convex. Why do I say that? Because if the f is strictly concave, if the lambda times g are strictly convex, then minus lambda times g are strictly concave. The sum of two strictly concave functions are strictly concave, so the Lagrange would then be a strictly concave function. What in God's name is this? Second, how do I do this? Oh, life. Here's how I do this. You now have n variables with k equality constraints. To check the second order condition, you form a completely different border Hessian matrix that you use for quasi concave and quasi convex. Notice, here's the way you read this. There are zeros. How many of them? K zeros, as many as there are constraints. Differentiate the first constraint with respect to x1, first constraint with respect to x2, first constraint with respect to xn. And then you keep going. This is the kth constraint, differentiate with respect to x1, kth constraint, differentiate with respect to xn. And now what you can see is that you now transpose this matrix. This is a k by k, right? So k and k. This k by k, take this k by n matrix, transpose it, so you now get this n by k. So this is simply, this thing is a transpose of that thing right there. And this, of course, is your n by n matrix. The way you sign this, so intuitively, if you have a maximum, you want, if this border Hessian matrix is negative definite, you have quote unquote a maximum. How do I check whether this matrix is negative definite? Completely different way than before. So I'll just focus on this one right here. To check when this matrix is negative definite, it'll only be negative definite if and only if the last n minus k leading principal minors alternate in sign, with the last leading principal minor having the summing minus 1 to the power n. So what happens is, intuitively, the last, so you start at the end. So, right, so find the value of n and find the value of k. Okay, and once, so let's say n is equal to 3, and let's say k is equal to 1. 3 minus 1 is 2. So what you would do is you would start with the last 2. So, it's a little bit hard to draw over here, but imagine you would start not with the last one, not with the last one, you would start with the last 2. And then what would have to happen is the leading principal minor of that one would have to have the sign minus 1 to the power n. If n was 3, that last LPM would have to be negative, and then it would have to be, then the one before that would have to be positive, etc., etc., etc. Let's do an example. You'll also solve this problem. 3 variables, 1 constraint. Okay. Solve the thing. You can show that the solution is x is equal to y is equal to z is equal to lambda is equal to 1. You wonder if x, y, z, lambda equal to 1 is in fact a maximizer or is it something else? Since n is equal to 3 and k is equal to 1, your bordered Hessian matrix consists of the following terms. Here's the only constraint differential with respect to x, y, z. Only constraint differential with respect to x, y, z. And of course, here's your Hessian of the Lagrange equation function. When n is equal to 3 and k is equal to 1, I have to do the following. I have to, by this thing right here, I have to check the signs. I start by checking the signs of the last n minus k leading principal minus. N is equal to 3, k is equal to 1. So 3 minus 1 is 2 leading principal minus. So here's your entire border Hessian matrix. So I check the last one, I may have, by the way, misspoken when I drew this slide. Sorry, guys, I'm getting tired. So if you had to check the last two, you would check last one and, of course, the one before. So in the same way, you now have the last two leading principal minors. Of course, the last one is, of course, the entire matrix itself. Check whether that one has a sign what? Minus 1 to the power n. N is equal to 3, so you would have to check if the last one is negative, right? Because odd number, no? Minus 1 to the power 3 is negative. And then the one before that, which I've given to you over here, would have to be positive. Those are the only two things you have to check. That's all. So last two leading principal minors. Last one has negative, and the one before that should be positive. By the way, the proof of why this matrix is necessary starts here. It's completely optional. This is for those of you who are serious about grad school. You want your money's worth. You want to come out feeling like a gangster 1 year later. One, two, three, four, five, six. Jesus Christ. Okay. Now we do multivariate versions of inequality constraint optimization. Here's a simple example. Maximize this function, subject is constraint. You can follow along the logic over here. Notice I don't take the derivative with respect to lambda. I do write down the Kuhn-Tucker conditions. Just like before, there are two cases, and you can go through this yourself and find out that this is in fact the answer, because those violates the Kuhn-Tucker conditions. What about the F of C's, S of C's, and all stuff? Good news, it's exactly like what you did before. So if you want to solve a problem with the inequality constraints, again, you have to find an x stars and lambda stars satisfying those differential the Lagrange with respect to the x's and the Kuhn-Tucker conditions. Again, I realize that this is a typo. It should really say, how do we know the x stars and lambda stars satisfying these things up here is a local max? And once again, you use the exact same bordered Hessian. But the difference now is that bordered Hessian only consists of binding constraints. So in this problem, you may have begun with k constraints. In the end, only let's say k over 2 constraints bind. Your bordered Hessian would only consist of the k over 2 binding constraints. So you would only form the border, this border of the constraints that are binding. So I didn't have to say this earlier because in the previous equality constraint problem, all k constraints were by definition binding, right? So I didn't have to say that over there. But this time I do. So in the next slide, if the fact that I wrote this down means that I'm assuming that all k constraints have ended up binding, right? They don't have to. If there were k, if only two of them bind, if only one of them binded, I would only have the first, this row over here, and this column over here, and this would be much, you wouldn't see this part right here, right? So assuming that this board has the matrix is drawn for all k constraints, inequality constraints binding. The logic is exactly the same. Nothing changes as long as you remember the border only consists of binding constraints. Example, the problem that you did 2 seconds ago, but this time with an inequality constraint. Okay. Again, the solution is x, y, z, lambda is equal to 1. Again, you want to know if this is a max or a min. And again, now the board Hessian with only one constraint, which by the way happened to be binding constraint, you would then of course form that you would differentiate that one binding constraint with respect to x, y, z. Now, just out of sheer curiosity, what would actually happen if this constraint did not bind? If it did not bind, lambda would be 0 and would become an unconstrained optimization problem. So you wouldn't have this border G over here. You would have simply the Hessian matrix itself. Beautiful, no? So you can go from the border Hessian to the Hessian because the borders only consist of binding constraints. So if you have no binding constraints, you get the pure Hessian matrix. So this one, you do have a border. And now, again, but the same thing over here. I have to check the signs, the last n minus k, 3 minus 1, 2 leading principal minors. The last one should be negative. The one before that should be positive. And in fact, you can verify on your own that in fact it is in fact the case. You should know how to do these determinants, by the way, right? Obviously. Here's a summary. Here are some serious problems. Thank you very much. I'll fix the slides with those little tiny typos I made and upload them. Thank you.